In this video, we'll explore how we could use mass spectrometry data to learn about the mass and therefore molecular formula of organic substances. As you're approaching your unknown identification in week 4, you may know the functional group present and the unique types of carbons, but you still may not be able to narrow down your list to just one possibility. Consider molecules A and B. They both have a ketone functional group, and they both have 5 types of unique carbon. So after week 3, I would have a hard time just differentiating these with the data that I have. Obtaining mass spectrum for our unknown allows us to match the mass of our unknown to the mass of the potential compounds. And you'll notice that even though they both have 5 types of unique carbons, compound A has an additional carbon and thus would have a higher mass compared to compound B. Before we look at the specific information we're going to be able to get from a mass spectrum, let's take a quick overview of how this technique works. So your sample is going to be introduced into the gas phase and then ionized by a stream of electrons. During ionization, your molecule can either gain or lose an electron. When your molecule loses an electron, it becomes a radical cation, shown here. The instrument we use and the data we're going to be looking at is particularly analyzing these cations. So on the schematic, you can see that neutral fragments and negative ions are excluded from analysis, while the positive ions of interest are propelled through an analyzer tube and towards a detector. En route to the analyzer tube and detector, the ions are exposed to magnetic fields of varying strengths. This enables a separation based on the mass to charge ratio of the individual ions. So the ions are encountered by the director as unique mass to charge ratios. And the data that we observe shows a unique signal for each unique ion. For us, the small molecules we work with tend to have a charge of 1. So mass to charge is represented as m over z. When z is 1, the value of the signal observed in our mass spectrometry data represents the mass of the ion that produced that signal. The detector for our mass spectrometers is very sensitive, so we can use a very small amount of sample, and it's highly precise. Thinking about the way we said the instrument works, it's also producing a signal for each individual type of ion that it encounters. So we have to remind ourselves about the presence of isotopes as we're thinking about the masses we would expect to see for particular molecules. You'll remember from your study of general chemistry that elements occur in nature as a mixture of isotopes. This table shows some of the commonly encountered isotopes in organic chemistry. For instance, you'll notice that carbon in nature is found as both carbon-12 and carbon-13, with carbon-12 accounting for about 99% of natural carbon atoms. In our mass spectrometry data, we're particularly going to see unique signals when we have isotopes possible that account for more than 1% of the natural abundance of an atom. So for example, look at Cl35 and Cl37. Cl35 is the major isotope accounting for 75% of natural chlorine atoms, but we have a substantial percentage of Cl37. Bromine exists as just about a 1-to-1 mixture of Br79 and Br81, with Br79 being slightly more abundant. If I have an organic molecule that contains bromine, for example, my detector will be able to distinguish an ion that contains a Br79 from one that contains a Br81, and I'll see a unique signal in the data for each of those molecules. So with that in mind, let's start to think about what we could expect to see when we look at the mass of ions for simple organic molecules. Let's start with methane, which only contains 1 carbon. On the x-axis of a mass spectrum, we're going to have that m over z value. Remember for us that z is often going to equal 1. And so the x-axis really tells us about the mass of the ions observed. The y-axis is ion count or abundance, and it tells us how many unique ions contributed to a particular signal relative to the other signals produced by the detector. So let's look at methane. When I'm thinking about the mass that I expect to see for an ion of methane, or any molecule really, I'm going to start by calculating that mass using the most abundant isotope at every atom. So I'm going to start with C12 and H1 to get a mass of 16. I say that that mass corresponds to my molecular ion, and I label that as M+. If I had 100 methane ions, based on the natural isotopic abundance of carbon that we saw on the previous slide, I would expect one of those ions to incorporate a C13 atom. So let's look at how that would change the mass. The mass should increase by 1 to 17, and I could place that on my spectrum as well. We call that signal the M+1 since it's one mass unit higher than M+. The height of that signal should reflect the isotopic abundance and the number of carbon atoms. I have a 1% per carbon, and I only have one carbon in my structure. So I tend to see this as a smaller signal at about 1% the height of the 16. So we could carry out the same analysis in predicting what we would see for a molecule that contains a bromine. This is bromobenzene. Following the same logic, I want to start by considering the mass obtained by having the most abundant isotope at each atom. 6 carbons, 5 hydrogens, and 1 Br79 give me an M+ of 156. We know that bromine has this distribution where about half of bromine atoms encountered will instead be Br81. So if I account for the presence of Br81, I would instead observe a mass of 158. I call that the M+2 since it's 2 mass units higher than my M+, and I'm going to place it right here on my spectrum. And I'm going to indicate that it's just slightly shorter relative to the 156, which accounts for our 2 isotopes of bromine here. I call these the twin peaks. When you have bromine present in your sample, you're likely to observe this signature pattern where you have an M+ and a nearly equal in height M+2. So when you're looking at your unknown data this week in lab, and you identify the molecular ion, you can confirm the presence of bromine if you see this signature. Beyond just predicting the M+ we expect to see, we can also take a look at some real data and use our knowledge of isotopic abundance to analyze that data. So here's the molecule benzyl chloride and the data obtained. Much like you're going to do this week in lab for your unknowns, I would shift your glance to the peaks at the farthest right, so the highest M+ value. And I see that I have these peaks at 126 and 128. So these likely correspond to ions of the intact molecule benzyl chloride. And I feel confident in saying that there's a chlorine present because I see the 2 peaks representing the natural isotopic abundance of chlorine, which is about 3 to 1. So when you see this, you can differentiate the presence of chlorine and bromine. And if you never see this in your data, it does not support the presence of chlorine. You may be noticing in this real data that in addition to the signal we're most focused on, the M+ at the far right of the spectrum given, we see these smaller molecular weight signals. These result from fragmentation of our ions, and we'll discuss them just briefly at the end of the video. Before we do that, there's one additional atom that gives a unique signature in the mass spectrum, and that's nitrogen. When we have an odd number of nitrogen present, we tend to see an odd M+. So here in this data, our M+ is 73. The odd value specifically for the M+ indicates the presence of nitrogen. So if your IR data and your solubility data had indicated that you have a primary amine, you should not be surprised to encounter this odd mass. We could consider a hypothetical scenario like the one we did at the beginning of the video, where I have an unknown and I know it has an amine. I know it has 3 types of unique carbon. I might be considering a list of possibilities and encounter the blue molecule and the green molecule. They both contain 3 types of carbon and a primary amine. The mass will be essential in differentiating them. If I look at the molecule in blue, I would expect an M plus equal to 59. Whereas when I look at the molecule in green, the M plus matches at 73. So this allows me to confirm the identity of the green molecule. Let's revisit the idea of fragmentation just briefly to prepare you for looking at real data. This is another spectrum for the molecule pentane. If you tally up the mass of pentane using the most abundant isotope, C12 and H1 at each position, you'll obtain a mass of 72. So we do in fact observe the M plus. What this particular spectrum shows us though, is that the M plus may not be the only peak and it may not be the tallest peak. So remember, we're generating ions, which are less stable than neutral molecules. So in the mass spectrometer, these ions can quickly decompose or break down. And we see these fragment masses for the pieces into which they break down. The base peak is referred to when you have a peak that is taller than the M plus itself. So the tallest fragment is typically called the base peak. Here in week 4, we're really going to be focused on the M plus, and you should each see an M plus that matches one of the compounds you're considering based on your week 3 data. In addition, you can use those bromine and chlorine and nitrogen signatures that we discussed earlier in the video to help differentiate your structure. And sometimes you may even see the bromine and the chlorine signature carry through to any of the fragments that also have bromine and chlorines. And one caution for nitrogen, the odd number value only applies to the actual M plus. You may in fact have odd numbered fragmentation as we do here, a mass of 43. That does not indicate nitrogen. That's just a result of the breakage that has occurred. So the odd number only applies for the M plus itself. So you'll start to get some practice using these in lab, and we'll revisit mass spectrometry several times this semester, during which we may delve a little bit more into some of these other complexities.